All right, we have just finished our inference with proportions. So we went through one proportions and two proportions, and then we also talked about the possible errors and then what power is related to that. Now, errors and power have to also do with means. So we will see that, we'll bring that back with our means. But now we're going to go into making inferences about averages. Not proportions of things, but averages. Well, there's something particular that is a big deal when we deal with means. And so let's take a look at what that is. So we see here, the t-distribution describes the standardized distances. So it's going to make a curve. Distances for sample means, seeing how far those sample means are from the population mean or the hypothesized mean. When the population standard deviation is not known. This is the big deal. You need to know that this is the reason that we have this thing called a t-distribution, not the normal distribution anymore. So, holy moly. No z-scores, t-scores. So, what happens is that we can hypothesize a mean, but the population standard deviation, figuring out on average how far is everything away from that hypothesized mean, that's near but impossible, almost impossible to actually have that population standard deviation. Therefore, we use the next best thing. Remember with proportions, when we didn't have true p, the best it could be is if we use true p, but if we didn't have that, we use the p hat. So it's the same idea, but we have to use what's called, the standard error. And so what we have is this, the standard deviation is now we're going to be using, so this standard error is going to be that standard deviation of the sample. And then for sampling distributions, remember we have the population, and then we drop down. Remember when we dropped down all of those means? Well, now we're going to use, then we're going to then how the means of those. In fact, I could pull that up real quick and show you that because I don't want to rush through your understanding. So if we go through, let's see, where's my sampling? There it is. Okay, so when we pull this up, remember this. So this was our population here. So even if we don't know, remember central limit theorem says even if we don't know what this is, then when we pull down samples that are large enough, then we will get a normal distribution. Well, technically, if we do not have this population standard deviation, then our distribution here will be a little bit more varied because we're not real sure about what that population standard deviation is. So we'll have a distribution that's a little more varied. Now in this applet, we do have the population standard deviation. So we were able to say, okay, this is our normal model, and we can use z-scores and such, but not really in the real world if you have this standard deviation of the sample. Now, remember that this shape down here is made up of all the little X bars, these sample means. So this was our sampling distribution, the X bars, whereas this up here is made with the little X's. Okay, if I had made this normal, let's say I had, if this was normal or whatever, it doesn't really matter what it is, because if the sample sizes that we take are large enough, then it's going to come out to be approximately normal anyway. But when these were individual X's in the population, X bars in the sampling distribution of samples. So we want to continue to keep population, and sampling distribution straight, because we're going to see all of those things come back. All right. So that was kind of a review, a remembrance of what's going on with that. Well, what happened is there was this guy, and his name was Gossett, William Gossett. He actually worked for the Guinness Brewery Company in Guinness, Ireland, and he figured out, hey, if we do not know the standard deviation of the population and we just know the one for the sampling distribution, then that means every sample size really has different amounts of variability. And you could see that here if we were going to be dealing with this. So every sample size is having the different amounts of variability. So what he did is he put the calculus to it, and he did tables and tables and tables of data, tables and tables, many calculations of all of the different probabilities for all of the curves based on every single sample size to a certain extent. Once they reach a certain point, they start becoming very small, minute differences, and we'll talk about that in a minute. But so this guy named Gossett, he wanted to publish those. Well, the Guinness Brewery Company wanted to publish those and make a profit from them. And he did not want that to happen. So he decided to publish all of those tables that contained all of the math to do the areas for every single one of those curves, those T distribution curves, and he signed it student. And then that T at the end was real prominent when he assigned it as a student of statistics. And he then distributed it to the world, and it was out there for free. And then the Guinness Brewery Company couldn't make money off of it. Well, that's how they became the T distributions, from that T in the student T tests and T distributions. Okay. So let's take a look at some qualities of these T distributions. So since we only have the sample standard deviation instead of the population, we must allow for the extra variation, the shape modeling the T distribution rather than the normal model. See, look at this Mr. T. I pity the fool who doesn't have the population standard deviation, because you're going to have to deal with Mr. T, the T distribution. If you do not have the population standard deviation, you're going to have to deal with Mr. T, the T distribution. So a larger N, we know, is of course less varied. So look at this black curve here. You can see that it has a degrees of, and we don't know what this thing called degrees of freedom are yet. And we'll talk about that. But it has degrees of freedom infinity, and we'll talk about what that means in a second. And so those are, once the sample size gets to infinity, then that's basically going to be comparable to your normal model. Okay. If they were smaller, then they are more varied. And you see here that these degrees of freedom for 3 versus 6, and we'll talk about what those means, but they are related to the sample size. In fact, the sample size, degrees of freedom is sample size minus 1. So this DF of 6 means that the sample size was 7. Okay, and again, we'll talk about that in a minute. But each one is different from the standard normal curve. And now when n is greater than or equal to 30, then those T distributions are they're very close. They're getting closer and closer to the standard normal. T distributions with just a few degrees of freedom have much fatter tails than the normal model. So degrees of freedom are based on the sample size and is defined as df equals n minus 1. So this is going to tell us which T curve to go look up the math for. So again, degrees of freedom, n minus 1 comes from sample size minus 1. That's going to tell us which T curve to go get the math from. Okay, so what is this thing called degrees of freedom? What in the world is that? Well, let's talk about that. What are degrees of freedom? You can think of it like they are the freedom to vary. Um, and so they kind of allow you to play it safe. They talk about how much choice and freedom you have for the variation on that. And I found this little video, and I really like the first minute of it. The first minute of this video, I think, does a really good job of explaining that. So we're going to watch that. Here we go.
This is an introduction to degrees of freedom. The easiest way to understand the concept is to think about calculating an average, or a mean. Presume that you have 4 scores with a mean of 50. That means that the sum of those 4 scores has to come out to 200. So let's choose our first score. Well, it can be just anything we want. Let's say it's 70. So our running total at the moment is 70. Our second score can be anything we want. We're totally free to choose our second score. So let's say it's a 20, which brings our total to 90. Again, we're totally free to choose our third score, say 45, which brings us up to 135. And at this point, our freedom stops. We cannot have any choice on that last number. It has to be 65 because the sum has to come up to 200. So essentially, when we're doing the average of 4 scores, we have 3 degrees of freedom. If we had 10 scores, we'd have 9 degrees of freedom. We're totally free for the first 9 numbers, but the 10th number is forced on us. In general, when computing an average, if you have n scores, you have n minus 1 degrees of freedom.
Okay, so that is a very simplistic example. And I have this article here that I'm not going to go through, but it's similar with the hats. If you had these 7 hats, then you can't, the first 6 days, you have the freedom to choose. But on that 7th day, I guess there were 7 hats, but on that 7th day, whichever one is left, that's what that's what you got to wear. You don't have a choice. So your degrees of freedom are n minus 1. Now, take a look here at, again, we have a few different curves. And so what I want you to do is go through these little questions that we have down here. Let's take a look at them. Which one of these curves, of course, I have it written in there, but if you did not see this, could you even tell what the highest degrees of freedom, which one of these curves would have the highest degrees of freedom, and how do you know? Okay. Next question. Which of these curves above has the largest amount of variation, and how do you know? Okay. Largest amount of variation. How about this? Which of these curves has the smallest critical value? That is a T star, not a Z star anymore, but a T star for the 90% confidence interval. And how do you know? So think about that for a minute, and then we'll take a look at those answers. So, of course, curve A, it says that the degrees of freedom is infinity. So, of course, that has the highest degrees of freedom. But even if we did not have that shown to us, we would be able to tell it's curve A, because that one is the one that's narrowest and skinniest and most closely clustered around the center, with standard deviation, or most tight standard deviation closest to the normal model. And so that's why it would be the less varied one, the highest degrees of freedom. Okay, so then the opposite of that, the fattest tails, are the ones with that is the widest and the smallest degrees of freedom. So this curve here, it looks like curve C is kind of smaller or lower in the middle because it's all pressed out. You have more data pressed out to the outside edges, and so that was the lowest degrees of freedom. Okay, now what about this last one? It says, which one has the smallest critical value for 90% confidence? Well, I drew 3 different colors of 90% confidence intervals in here. So on this curve A, 90, since it's most closely clustered to the center, its critical value, its T star, well, in this case, if it's degrees of freedom infinity, I guess that would be a z star because it would be like the normal model. So there that is. And in fact, look, I placed it at negative 1.645. So see, I did do that at that place. Okay. Now for curve B, which is a little bit more spread out, so that's this green color I have here. So see, look, those T stars are a little bigger because they are more spread out. They are farther away from the center. And then finally, this curve C, that is the widest and the fattest, the lowest degrees of freedom, most varied, has the widest 90-degree confidence interval. And so the critical value for those are the largest. Okay, I don't think I actually computed, I could have computed those critical values. I don't think I did for those ones, so I'm not sure the green and the red are in the exact correct place. Okay, so here we go. We have a song to remind us that when we have means, we use T distributions. And it says, so this is kind of like a little group participation. Who's got a mean test? T, 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 not Z. And I won't be able to actually sing it with you with the video because the way that the video works when I'm recording it live, it's kind of out of sync. And so I cannot sing with the video when they do that. But who's got a mean test? T, 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 not Z. And look at what I say here. Sample standard deviation. That's the reason that we have a T, 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 not Z curve that we have to use. Who's got a mean test? T, 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 not Z. Now look at here. Must include the DF. Why do you think on every problem, it will, when we are dealing with means and that sample standard deviation, it will be important for us to include the DF, the degrees of freedom, in our work? Why do you think? Well, you have to tell the public, the reader, whoever's getting this information, which curve you're computing and your probabilities were computed from, because they're all different based on the sample size. So you must state what degrees of freedom you used. Okay, so let's do our little video on that, and then I think before we get into the math and some calculator stuff, we're going to start a separate video because we don't want these to be too long. So here we go. Oh, I wanted to show you. I had this here. Let's see if I can get this to open up. Um, let's see. All right, here we go. Here we go. Here we go. Oh, I don't know. Let's see. Okay, so this is going to be an actual picture of what's going on. And let's see if this will come up. Here we go. Okay, this is cool. This is going to be an applet and show us what's happening with our degrees of freedom. So look here. Let me go ahead and put the normal model in there as well. So you see this red curve, that is the normal model. Let me go ahead and get us some smaller tails because we usually don't deal with tails that big. All right, so here you can see the black curve is the curve that is wider and fatter. And then as my degrees of freedom increase, it gets closer and closer to the red curve. Okay, so here's this. It's slight difference, just a slight difference here. So as my degrees of freedom increase, there's degrees of freedom 3, 9, 10, and so on and so forth. And you can even see the percent difference, the percent error between the area of the normal model and the T curve. So there's a little bit different percentages that you are getting in these tails from the T curve versus the normal model. And look what happens as I get my degrees of freedom bigger. This percent error, this percent difference between normal and T curve is getting smaller. So increasing that, I don't think, see, I won't be able to go to infinity, so I won't be able to get this down to 0. But anyway, so there you go. So there's kind of a visual demonstration of what's happening to our t-curves. Okay, so let's move on to our song and let you hear that. Here we go. Got the mean girls for our mean test. All right, here we go.
Who's got a mean test? T, not sample standard deviation. T, not Z. Who's got a mean test? T, not must include the DF. T, not Z. Who's got a mean test? T, not sample standard deviation. T, not Z. Who's got a mean test? T, not Z. Must include the DF. T, not Z.
All right, there it is. Okay, so let's go ahead and take a look. We don't need to hear that again. All right, let's take a look at our next page and see what we have going on here. So this is just a side-by-side comparison of the symbols that we're using and the formulas for proportions versus means. Okay, so let's compare those. So remember that for proportions, when we had a sample proportion, it was a p hat. And then when we have a sample mean, it's an X bar. Now, I think one thing I did not include here, what about population? A population proportion was a capital P, and the Greek letter mu is the population mean. Okay? All right, now here, then of course, so you know what's going to happen. You remember if we were going to do a confidence interval and we had to get that critical value, we do not do a Z star and do inverse norm of one tail. Now we will do a T star, and we have to do inverse T is in the calculator of one tail, like we have been doing, but you must include the DF. You have to tell it which curve your critical value is on. Because remember, on this picture here, it's a different critical value depending on which t-curve you're computing it from. Okay. And so then, of course, our standard deviations here. Now, I have this written with sigma, okay, but we really do need to think in terms of if we were doing this with a sample standard deviation, then what's going on? Okay, I have no idea. I have no idea why that just came up there. But if we were doing I do know. There's my keypad. So if we were doing a sample standard deviation, we would have the S of X, okay? And we would have the sample standard deviation of the X bars, okay? So that's like whenever we're doing, I guess I don't have that whenever we're doing the sampling distributions, okay? So down here, this blue one, sampling distribution standard deviation. Okay. And so then look at our Z star, when we do a test and we get our Z score, that's your P hat minus the mean of P hats over the standard deviation of P hats. Well, for T, it's going to be that X bar, seeing how far that sample is away from where it is claimed to be centered, but in terms of the sampling distribution standard deviation. Oh, and then if you're going to get the area in a tail, so remember, once we would get a Z-score, we would norm CDF from the low Z to the upper Z. Well, now we TCDF from the lower T to the upper T, but you must include the DFT, T, not Z. So when your calculator is giving you an error, then it could be because you left off DF, the degrees of freedom. It has to have in there. Okay. So we've got our confidence interval, is the statistic plus or minus that critical value times that standard error of the statistic, which we put a S if it was our standard error made from the sample standard deviation. So there you go. So I just wanted to equate those two things together. And so I'm going to stop this video here. And on the next video, we're going to actually do the calculator computing for getting the t-scores and getting the areas, calculating the areas for the probability based on a t-curve. Okay, so get your calculator, and I'll meet you in the next video, and we'll do some of those calculations.